course. So we were sacrificing so-called nonadiabatic couplings, which you do not need if you are describing materials at low temperature, and if you are not interested in, say, combustion reactions and high intensity laser field or some intense exotic processes, which we will do for about 20 minutes. So but at the end of the course, we may want to return back to discuss this nonadiabatic couplings, and if we decide to focus on some exotic chemical reactions. For this purpose, you are invited to remember equations related to nonadiabatic coupling, summarizing the whole work. Another concept, and I suggest we just chat informally and then I'll show you some slides. Another accomplishment of consequence of our consideration before is that electronic and nuclear degrees of freedom are decoupled in the limited sense. They are decoupled in a sense that there are no change of electronic state due to nuclear motion. This is what we measure. But still, nuclear degrees of freedom depend on electronic state and electronic rearrangements. And if there is a term, potential energy term, contributed in addition to nuclear repulsion, there is an additional force on nucleus because of the certain electronic state of a molecule or a material. And if we add together this nuclear repulsion energy and the energy contributed from electrons, it will be dependence of potential energy on positions of nucleus, and it is what we refer to as potential energy surface. We will talk about it again, and you may have experienced this before in your molecular dynamics things. But if you go online for the Wikipedia article or summarize your personal perception of what potential energy surface is, just provide some definition, give you another little thing for homework. You do not need to waste time, just write a sentence and draw a little figure. Okay, now we know from those of us who are enjoying the molecular dynamics know that Newton equations of motion for just pass it around. If you're bored to listen, you just something else. You know that applying Newton's equation of motion to positions of nucleus is really powerful, comfortable, and fruitful concept. And we are not going to decline it, although we have introduced some quantum features. It would be good to look on the interatomic distances in the same framework as one does in molecular mechanics with classical field transport. So we are going to discuss the subject a little bit today and focus on how it is going. So the goal is to return back from this Schrödinger equation with quantum features into equations that look like Newtonian equations of motions. But we need to recognize what we are neglecting. Definitely, the Newtonian equations of motion are less precise, and we need to recognize the limits when it is possible. If you agree on with this idea, then basically we are very good. And there is a background concept of quantum theory that allows to do this transition back from from Schrödinger equation to the Newtonian equation of motion. It is called Ehrenfest theorem, and this is not a subject of what we do of the class, but I will refresh the theorem if you had it before, or introduce if you didn't have. You do not need to be strong in derivation of these concepts and theorems, but to be aware of their existence is a useful thing, so that, for example, you present an oral talk on a conference or a poster, and the audience asks you, how do you justify use of Newtonian equation of motion here? And you tell, like, based on Ehrenfest theorem, it reflects some quantum properties. And it will be much more soluble. Or if you submit a paper to a journal or to a thesis committee, justification and referrals to the fundamental theorems will make your case stronger and help in more favorable consideration. So we are here next Tuesday. Next week will be fun. Tuesday will be fun for you. Thursday will be fun for me. On Tuesday, we will discuss the algorithm for optimization of molecular dynamics, and we will play robots. We pretend that each of us is a little robot who does optimization problem. And here's the list. I plan to fill the gaps by suggesting someone to take the gap among those who didn't take. And I'll try my best to send you examples of presentations from previous years that you can use as an inspiration to see how things look like. But there is a quick comment on the presentations. Those are not academic summary of information that you find in books or in the internet. It will be sharing your personal experience, sharing your success or failures in operating specific software, in trying this exact concept, like show screenshots. I typed this command and I got an error. Do not do this again. Things like that. So your personal experience. Because for going online or for reading manuals, it is all of us can do, but your personal experience is a very precious thing that you can share. Okay, we went over this a little example, and we are first. This molecular Schrödinger equation is electronic contributions here, and here's the kinetic energy that we did process and agreed to have the theta AB nonadiabatic coupling, which is a response of electronic wave functions to the change of nuclear positions multiplied by momentum of nucleus. So if there is no momentum, there is no motion, nonadiabatic coupling is zero. If the wave functions do not change, if you move ions. For example, if you have electrons and no ions, there is no this coupling. And so this is a couple of slides left over from previous meetings. I feel confident that we will squeeze everything and finish it. The goal is to get equations that look like Newton equation. We did stop on the quantum Schrödinger equation and independent Schrödinger equation for chi, for nuclear wave function. Nuclear wave function is amplitude of probability to find each nuclei at a certain place, and it is not exactly a point in space, but distribution around. if we assume that our nuclei are allowed to move, it's not just distribution, it's dynamics, it's how these distributions change in time. And then we go from the time-dependent to time-independent Schrödinger equation, which has the same operator of total energy, Hamiltonian, but the wave functions accrues the dependence of time. And it's here in the third, and there is a change in time. Typically, in most practical cases, this wave function can be thought as Gaussian distribution with some fringes. And after today's lecture, we will make some points to consider that instead of Gaussian distribution, it's still localized point in space, like delta function. But we will cast a spell. We will verbalize necessary verbal formula to justify this. So the goal is to go from time-dependent Schrödinger equation for nuclear wave function to Newton equation. And this is look at this. Even if it is not labeled, you may recognize it. So it's nuclear repulsion plus contribution to energy from electronic terms, which we call, we just mentioned like 10 minutes ago, potential energy surface, right? Why surface? Why not curve? Because there are so many atoms and it is multidimensional. If it is either one dimension only or diatonic molecule, it's a curve. But if it is more than 2 dimensions, if there are 2 dimensions, it will be like 2-dimensional surface. And if it is more, it is something more complicated that it's not natural for humans to imagine, but mathematically it's fine. Multi-dimensional surface, dependence of energy and arguments. Oh, here it is. PES. Okay, so it is what we should have finished. Who recognizes these two equations? You know what I'm saying. If you feel comfortable with them and can explain them in your language. Even if you are like halfway comfortable, give me a real sign so that I see. Okay. Give me a sign if you have no idea what it is and if you are like protest and object against these equations. Do not hesitate. We are like colleagues sitting in the same boat. Raju, can you briefly tell what you think about these equations?
The first one is the derivative form of position. So the P represents the angular momentum. So
just momentum, not angular.
Sorry, just momentum. So if we put that P square by in the form, then we'll get dr by dt.
You are thinking of putting this one into here.
Yeah.
Everyone follows the idea? Or more explanation?
It's a derivative form. And the second one is just the derivative of momentum with respect to time, because we know the work is just momentum is a change, just a work, force into distance.
And I'm specifically interested in your suggestion to plug in this equation into here,
yeah.
or maybe to combine. Why you mentioned to combine these two equations?
Because it's easier to get the second equation. Because
like if we replace P here with this part of the equation.
Okay, so
and if you want, you can either explain or write down on this screen.
so just the P bracket equals n, and yeah, just this one. Okay.
Divide it.
Divide.
Okay.
So if we put here, so it's gonna be like
maybe next line.
Next line. Okay, so it's gonna be n p squared by dt squared and r here. Okay. So this represents acceleration. So from there, because we know the F equals mass into acceleration. Okay.
Is it better now?
This is a Newton's formula.
I will add more comments, but do you feel the general direction where wind is blowing?
Okay, and E equals d squared r by dt squared.
Good. Excellent. Thank you, Arjun.
But I have one confusion, is that how is mdr by dt equal to md square r by dt square? How are those two products?
Okay, let me do it carefully, and Raju did everything in the right direction, but let's fix the details. And it's not the original plan to focus on this equation, but there is no reason to go further before we agree on basics. So what I suggest, we use this definition, which is just a follow-up of the first equation, right? So we multiply left and right part by mass. Good. Now we do have definition of momentum. Not definition, but like connection. Momentum is mass times velocity.
Yes.
Good. Now let's plug this momentum into here under the differential sign. So I'm rewriting the second equation. I'm doing d dt, and here instead of p, I will write this one. Mass times d dt of r. Equals f. Right? Now you can put mass out of brackets, and then it will be second derivative of position. Second derivative of coordinate is acceleration. So a, m times a equals force.
So why is there still a branching for r?
Good question. We do need a concept of expectation value. If we are speaking on a language of like classical physics, position, momentum are like variables. Right now, we are sitting on the top of the mountain of the knowledge of quantum theory. So we never again neglect the fact that the knowledge that there are wave functions, so that even a nucleus, one atom, has one nuclei has distribution of the inherent there. But we can assume that the nucleus is distributed, but we can tell that approximately it will be in the center of this distribution. Or expectation value, average, or in average where we will find it. And this average is symbolized by this brackets. So we still we are telling to everyone we are knowing about quantum properties, but we are not going to tell the whole story of the distribution. We are going to focus on the average mean position of each atom of nuclei, which is symbolized by these brackets. And now we are writing down equations for this expectation value. Make sense? And it will be equation very similar in functional form, exactly reproducing Newton's equation of motion, but the meaning of this position is different. It's not a certain position; it's expectation value position. Why we use two equations instead of one? Is there any benefit, any reason? Because we all are so comfortable with second derivative and standard way of force is equal mass times acceleration. Why we need to replace one equation into two? Is it a silly step, or there is any reason behind it?
We have to simplify.
Yes, it's simpler. First order equation, first order derivative, even if there are more equations, are much easier to propagate numerically. If you do second derivative, a chance of error is higher if you write a code to solve it. For first order derivative, it reduces chance of an error.
More linearity.
Right, exactly. I already forgotten what to do with that on the next slide. I'm curious myself. Okay, good. So, you did derive this equation. Well, we all together. So it's like Newton equation of motion, but it is for expectation value of the position of each nucleus. Let me. I'll quickly write down because of the question. So R equals integral chi of R times R d R. So it is used. Oh, it is the same as written here. It is what is used here. It is what is used there. So if we use a continuous function, we just integrate distribution function times the variable that we need to find expectation value of, integrate and get this brackets. If we want to look smart, there is an equivalent representation of here when it's the absolute value squared, because it is probabilities squared of a function. The alternative representation of this equation is here. Bra of the vector variable, cat of the variable gives this expectation value. So this angular brackets, Dirac notation, are equivalent to this integral notation. So what is the slide? Basically, if we agree with the goal of the meeting is to arrive to this slide. If we agree on each symbol there, the rest can be skipped or can be just quickly skipped through. We do have a more piece of material that we want to know. We already accepted Born-Oppenheimer approximation, giving up nonadiabatic couplings, and then we do have Schroedinger equation for electronic wave function and Schroedinger equation for nuclear wave function. We are going to jump from nuclear wave function to expectation value of position of each nucleus. And then, using several theorems, one can find what will be the force acting, what will be analog force that will be a reason to change this expectation value of position. And if one accepts these theorems that we'll go over, then one can set up equation of motion either in form of a pair of equations or as a single that will resemble the same form as Newton equation of motion. But it will include interaction with electrons. It will include quantum nature of nuclei. And there is a way to make it a little more precise or add terms that will describe more quantum properties. So in the yellow box, it is a set of equations that one typically solves. So one keeps thinking of electronic degrees of freedom as wave functions and solves Schroedinger equation in one or another variation, in one or other approximation. But for nuclear degrees of freedom, one is speaking on expectation value of position. The error of neglecting the shape of this nuclear wave function distribution is often accepted. There are some certain limits, like Raman spectroscopy, when one specifically needs quantum corrections to nuclear degree of freedom. But for like 95% of problems, it is okay to tell that instead of nuclear wave function, for each nuclei we have just one vector. Good? Yes?
So the electronic wave function is time independent and nuclear wave function is time dependent.
If your question is very legitimate. Electronic wave function is time dependent. And if we will look on transition phenomena, again, combustion, photoexcitation, maybe photovoltaic or photodiodes when you photoexcite something and then things rearrange. Then of course one needs to use a time-dependent Schroedinger equation. But in case we are focusing, it will be important if we are looking on like femtoseconds, like 10 to the minus 15 of a second. But if you're looking on minutes or hours in our human time, all electronic dynamics will be finished before that. And it is a good approximation to assume that electrons did relax to their ground state and we just find the eigenstate from the equation. Your question is very legitimate and we will go beyond that. But if you want to use majority of textbooks, we should stay here. It is like standard pathway.
Yeah.
Okay? Good. Any objections, complaints? Okay. I hope you're not yet very tired and in fact, we are starting the lecture. So there will be some equations which can be considered as unpleasant or boring. Just get ready and administer your own intellectual effort, whether you want to focus on them or just lay back and sleep. It's your project. So the potential energy surface is like how the energy depends on the position of nucleus, and it will be slightly different for index B. depending on which electronic state we are exploring, the forces will be a little different. Nuclear wave function will have some shape, typically just one hump with little fringes. Gaussian form. All the things about nuclear degrees of freedom, expectation values, molecular dynamics are needed to complete one very basic and standard procedure, geometry optimization. I'm showing something from previous year, but you already tried it by doing cleaning, and we will do more of it when we meet next Wednesday. So if you draw a molecule by hand, you may draw something not ideal. The bond distances can be less than optimal. Right? And optimal means minimizing total energy. If you click on the optimization button, then it will quickly find most optimal independent distances and find the chemically relevant structure. And in some sense, all of our suffering, all of our efforts in the class are just needed to justify this procedure that we are doing now. I hate lots of text. I don't remember what I wrote here. Maybe it's reasonable, but we need to optimize. And the procedure is that if we are generally, so an optimization procedure for given, I can often forget to put this angle in brackets, and in literature they are not always placed there. But from now on, when we speak on positions of ions, we are speaking on expectation values. So for expected position of ions, one can find electronic properties, plug them into potential energy surface, and find how the forces will slightly change the ionic positions. And then we go in a circle until the system comes to a minimum and stops changing. Does anyone feels happy about these equations? Does anyone probably we don't care about it, but briefly, there is no reason to go with it, but it is a mathematical expression for Gaussian nuclear wave function of nuclei that changes in time. And it shows, you see this minus xi square, so it's typical Gaussian shape, right? And those are eigenstates of harmonic oscillator, and those are, this is Gaussian reflected when it moves. But one of the ways to simplify thinking, just to not to get crazy, is assume that nuclear wave function has a shape of delta function, that it is centered near the expectation value of nucleus. Okay. Main part of today's meeting is to go from time-dependent Schrödinger equation for nuclear wave function to Newtonian equation. This is done by so-called Ehrenfest theorem. And if you are not happy with I'm talking, I've sent you linked to Wikipedia, so it's like common knowledge. So the Ehrenfest theorem and more general concept of Heisenberg equation of motion deals with expectation values in brackets. Why these expectation values generally are needed? Why? So the concept of Heisenberg equation of motion and Ehrenfest theorem were designed at the very early stage of development of quantum theory, like at least 50 years before first computers were designed. So it's in some sense ancient concept. Why people did care about it? The goal of any natural science theory, and specifically quantum theory, is to predict outcome of an experiment, to interpret it or predict outcome of something that hasn't been experimented. And on all experiments, one is obtaining numbers. It is not common to set up an experiment that will measure a wave function, and it is not very practical. Right? So, if one knows wave function of a molecule or generally any system, there should be a way to convert wave function into observable, into a thing that comes out of apparatus from the instrument or experiment. And this procedure of finding expectation values is exactly what is thought. It is like this expectation values is a bridge that connects abstract wave function and real world. Remember, we were writing down this integral of wave function squared times r dr. So it is how to find expectation value of position. But for any observable, there is a way to find to implement this concept and write down the expectation value. And now we are diving in a little bit of background from quantum theory. The following idea can impress some of you, if I describe it in a reasonable way. Wave function is a huge monster. It has a lot of independent variables, and if you save it numerically, it will be a huge amount of data, like terabytes, especially if you have all the degrees of freedom. But at each specific time, if we describe a specific experiment, we need just one number instead of terabytes of data. Right? So we do have equations to solve for wave function, but then we are doing this convolution process that reduces terabytes of data into one number. Is there a shortcut to write down an equation for observable, for this one number that comes out of the experiment? Maybe for this number as function of time. So avoid terabytes of data. Avoid wave function completely. Keep it in our head, but remove it from calculation procedure, from the computer. So this idea came to the head of Heisenberg. They were like fellows and competitors. And Schroedinger is a little bit more famous because his equation is a little easier to perceive, and like, a lot of things were derived from Schroedinger equation. But there is a Heisenberg equation which is competing with Schroedinger and targets the same goal, to predict outcome of experiment. And what we are going to do today rests on Schroedinger equation of motion. So let me cover this story a little bit. In order to recognize use and benefits of Heisenberg equation, we need first to recognize way how observable, how expectation values are obtained. And they are, I will write between lines here, but I will have the next slide duplicating this. So if we have arbitrary observable and we do have a quantum operator for this observable, then expectation value will be integral times of independent variable, then quantum operator, which is typically like a combination of derivatives or stuff like that, and a function without star, and then the other. Otherwise, it is denoted in the Dirac notation. So, what is the meaning of this line? It means that we are combining our operator with wave function in two shapes. When it is without conjugation, it is equivalent to vector column. When it is with conjugation, it is equivalent to row vector. So it's like row vector times matrix times column. So bra is row vector, cat is column. In these notations, you see, I'm putting it here. In this
Row vector?
row and column.
Row and column.
Row and column.
Which one is row and column? Asterisk is row?
Just a second, just a second. Repeat your question.
Which one is row and which one is column?
So this one is column.
Static.
This one is row.
Okay.
So which means chi of R1, chi of R at position 2, chi of position R3, and here the same is chi of R1, chi of R2. So it's same numbers, elements of this function, but they are written either in row or form. So this implementation of this equation for expectation value uses bra and ket vectors. So if you plug in bra and ket vector into here now, and feel free to just lean back and relax. It is a complementary story that will just help major over the course. If you want to explore how the expectation value of a certain observable will change in time, on the one hand, we can just solve Schroedinger equation for bra and ket vector wave function, and then practice this equation again and again at each point of time. But it is a big waste of efforts, big waste of numerical data storage. What if we accept that we already have in abstract form this expectation value, and then just put time derivative in front? If you will be able to find this time derivative, it means that you will be able to find how this expectation value, which is needed for real observations, change in time. Now, derivative and three functions. Derivative of three functions is derivative of first function, two other unchanged, derivative of last function, is unchanged, and derivative of the middle thing and first and last unchanged. For simplicity, we forget this term. It's always possible to put it in. But first, these two things are important. It looks like a little lie. You came to computational chemistry, and now you are considering quantum theory. But it's just a little entertaining. You return back. So the time derivatives for the bra and cat are slightly different. For the bra, it is regular time-dependent Schrödinger equation. Time derivative of wave function equals minus I h bar Hamiltonian wave function. That we all know from childhood, so to say. But if we use this transposing of wave function from column to the row, and we also have this asterisk, means it is complex conjugate, imaginary unit accumulates minus sign. Okay. Therefore, we change from minus here into plus here. So the time derivative of the Bragg vector will have plus sign. And also, in order to keep the linear algebra properties, we are writing, we cannot multiply a row vector, we cannot multiply matrix by a row vector. It will be a crazy operation. Typically, we need to multiply a row by matrix from the front. Therefore, they are in different order, here and there. Okay. Any protests? Okay. I'm going to show this same slide without recent notes and with little highlights. So we'll continue the same thing and just re-show it. So I'm going to simplify this equation with knowledge of these two boxes. So here I am replacing time derivative of the bra with this stuff. Time dimensional equation for bra. Here I'm replacing time derivative of the cat with this time dimensional equation for the cat. From here to there, from here to there, to there. So here we have bra, a, cat. Here we accumulate this factor, sign, and also Hamiltonian. Right? We just get it from Schroedinger equation. Therefore, therefore here we get chi h a chi, and here because of the swap you get chi a h chi. Just plug in. So it is basically a ha-ha equation. So how do we interpret this ha-ha equation? Change of the expectation value of an observable is equal to ha-ha of its operator. And this ha-ha means swapping order between operator and Hamiltonian. And by quantum, often this commutation is not equal to 0. So what are the benefits? If one is able to write down this equation, to implement it for specific observable, for specific variables, then one can leave behind Schrödinger equation. Then Heisenberg wins. And we can save terabytes of storage. Right? So there's one number that changes in time, one function instead of wave function. And it is what we want to do. We want to apply this procedure to nuclear degrees of freedom, to describe only expectation values of positions of nucleus, to forget about nuclear wave function. Okay. So I know we are a little bit over time, but the plan is to plug in the position operator here and there and look what happens. last year there were volunteers to do it, but we'll do it a little quicker this year. So if A is position, then this Heisenberg equation of motion ddt of R, HR minus RH. And H is kinetic plus potential, right? R, kinetic plus potential. The potential energy...
Your call will be disconnected.
Doesn't matter, we are still on the record. It affects only those who was eventually watching it from far remote. Potential energy is polynomial of position. Therefore, VR minus RV is 0. V depends on R, V depends on R. So we need to practice only TR minus RT. R is position, T is kinetic energy. It is not like gas constant in temperature. No. Just avoiding ambiguity. Now, kinetic energy is momentum squared. So we need momentum squared times R minus position times momentum squared. So we have PPR minus RPP. Good? What do we do with it? How do we, is there a way to simplify it? What is R P minus P R in quantum theory? So instead of 0, it will be equal to Planck constant. So swapping the order of P and R gives this constant. And it is another like basics of quantum theory. And if we apply it, then PR and RP will be replaced by Planck constant, and we will have the momentum. So the time derivative of the expectation value of position equals Planck constant expectation value of momentum. And if we carefully process it, then we will, if you take care of the constants, we will obtain that time derivative of expectation value of position of nucleus is equal expectation value of momentum of nucleus divided by m, which is basically velocity. But so we reconstruct the definition of velocity and momentum, but it is not for points. It is for expectation values of wave functions. So it is basically this is Ehrenfest theory. And the same thing with a little bit more derivation is possible to be done for the momentum. So if you plug in definition momentum into Heisenberg equation of motion and carefully do all steps that we practice High equation for momentum, then we will obtain the force of the expectation value of position. And then we do have this set of equations for position and for momentum, and we can solve them simultaneously to get from the value of position and momentum, expectation value of position and momentum, at certain time to position and momentum of next time increment, delta t. So in some sense, we are reconstructing procedure of molecular dynamics. I hope we are arriving at the last slide. So meeting is done. Thank you for the patience. Have a nice weekend, and I look forward to seeing you next week. Thank you. I'll stay here and answer any questions. But everyone, needs to live with. Yes.
PR and RP equals I H bar. Schrodinger equation, right?
It's commutation of operators. If you take the P equals I H bar DDR, right?
Yeah.
And then you write down P R minus RP with understanding that it is a set of operators acting on the wave function.
Yeah.
So from here you get minus I H bar D R R chi minus R D R chi. Right? Now the derivative is applied here to a product of two functions, and here is R times derivative of the function.
Yeah.
So if you open this bracket here, you will get it will be dr over r will be 1, right?
Yeah.
1 times chi
1 times chi
plus r d chi dr minus r d chi dr. And then these two terms cancel, and we are getting minus I H bar. And the chi is, we just cancel it. But we will always keep in mind. So this is operator. This is set of differential procedures that act on unknown function.
Okay. Yeah,
Good?
yeah. Thank you.
Make sense?
Yeah, makes sense.